Let me briefly explain the framework of the auxiliary group. The flavor group GF is given as the direct product of the conventional flavor group denoted with GR and the so-called auxiliary group denoted with GX. Fermions transform non-trivially only under GR. On the other hand, the scalar field phi transforms non-trivially under both GR and GX. Therefore, in the fermion mass terms, the scalar field cannot couple as linear terms. We call phi the elementary field. We construct effective fields which are quadratic or higher order products of the elementary field, such that these effective fields transform non-trivially only under GR. So these effective fields can couple with the fermions and thus we construct the mass terms. In the previous video, we used this GF as the flavor group and we constructed the fourth order renormalizable potential using the field phi given here. A point that I forgot to mention at that time was that in this particular example, the symmetry group of the fourth order potential is the same as the original symmetry group GF. So I use the words GF and GF4 interchangeably throughout this example. GF can be written as the direct product of GR consisting of S4 cross Z2 and the auxiliary group GF, which consists of the rest of the groups. Now we construct effective fields using this elementary field phi. In order to do that, we define the matrices S and A, which are the symmetric and the antisymmetric parts of the product acute phi, hat phi, gray phi respectively. With these, we obtain the effective fields. They are given here. These are the multiplets of S4, which are also assumed to transform non-trivially under Z2. As you can see here, we need at least cubic order products to construct them. I use the letter psi to denote the effective fields. The subscripts 1, 2, 3 and 3 bar denote how these effective fields transform under S4. In these expressions, these k's are some constants and this lambda 8 and lambda 3 are the Gell-Mann matrices. We already obtained the stationary point of the elementary field phi. It's given here. So we can simply substitute this in the expressions of the effective fields here so that we can obtain the stationary points of the effective fields. Their values is given here. So they are Xi10C, Xi20C and so on. Let me use the word orientation to denote all degrees of freedoms of an irrep except its norm. If you examine these expressions carefully, you can see that their norms contain these constants k's as well as the norms of the irreps of the elementary fields denoted by these acute VSC, hat VSC and so on. Whereas the orientations of this doublet and the triplet is fully fixed. The orientation of the doublet -1/2 minus √3/2 is not very surprising. It directly follows from the symmetries of the 2 of S4, which is nothing but the dihedral symmetry of the equilateral triangle. On the other hand, the orientation of the triplet is very interesting. Let us study this orientation in detail. This stationary point contains two intrinsic constraints. The first one simply says that the second and the third components of the stationary point are equal. And the second intrinsic constraint says that the first component is twice the negative of the second component or the third component. Now we will see how these intrinsic constraints arise. We mentioned in the previous video that the elementary field's stationary point phi 0c is invariant under 4 group actions under this larger group G tilde F4. We can show that these 4 group actions constitute 2 dihedral groups, here denoted by d6 prime cross d6 double prime. And these 2 group actions together constitute a single group action under GF4, and that generates a Z2 group, here denoted by Z2 prime. The action of this Z2 prime on the effective field Xi3 is simply the action of the matrix U. And as you can see here, the stationary point Xi3 0c remains invariant under the action of U. So this invariance, it simply leads to our first intrinsic constraint, that is, the second and the third components of Xi303 are equal. What we saw here is that the symmetries of phi 0c under GF4, which is simply this Z2 prime, manifest as the symmetries of Xi3 But we also have additional symmetries of phi 0c arising under the larger group G tilde F4. By additional, I mean the transformations under this G6 prime cross G6 double prime beyond the Z2 prime group that I mentioned earlier. Now the question is, do these additional symmetries also manifest as the symmetries of Xi303? The answer is no. But why? Because when we construct the effective field from the elementary field, we utilize the fact that the elementary field is transforming under GF and not under the larger group G tilde F4. Therefore, the construction of the effective field in general breaks G tilde F4. Therefore, the additional symmetries of phi 0c beyond this Z2 prime do not manifest as symmetries of Xi3 0c. However, these additional symmetries are essential to generate our second intrinsic constraint. Because of these d6 prime cross d6 double prime symmetries, various errors constituting phi 0c, they get oriented in a very specific way. Information about their relative orientations get encoded into these components of the effective field Xi30Z, which leads to this second intrinsic constraint. That is, the first component is twice the negative of the second component or the third component. The effective field Xi3 transforms under the group S4 cross Z2. This group is the symmetry group of a cube having 48 elements. In the normalized space of a triplet transforming under the symmetry group of a cube, we have only 3 orbits which are isolated in their strata. This can be proved. These orbits are phase centers of the cube, which consists of points such as 1, 0, 0, edge centers of the cube consisting of points such as 1, 1, 0, and vertices of the cube, which are points like 1, 1, 1. The orientation 2, minus 1, minus 1 is not one among these. On the other hand, using the concepts introduced in this work, I have obtained the orientation 2, minus 1, minus 1 for a triplet transforming under the symmetries of the cube. Now you may ask, I have seen orientations like 2, minus 1, minus 1, or perhaps even more complicated orientations in Newtonian physics literature. So what is so novel about this? Now my answer would be, if you carefully examine those papers, you will notice that authors had to impose constraints on the coefficients of their potential to obtain their results. As I said before, that is not good enough for us. In this paper, I have shown that orientations like 2, minus 1, minus 1 can be obtained entirely from group theoretical properties, independent of any kinds of constraints that you impose on the coefficients. Of course, we cannot construct a flavor model with a single alignment 2, minus 1, minus 1. However, if you include a larger set of elementary fields and using the same concepts introduced in this work, it is in fact possible to construct a phenomenologically realistic flavor model. I am currently working on such a project. Since we are having more and more precisely measured Newtonian observables, and since perhaps we do not have any unbroken symmetries, I think these concepts that I have formulated will be quite useful in constructing models. I summarize the work here. We constructed the potential Vp of order P using the scalar field phi, transforming under a flavor group GF. We named the symmetry group of the potential VFP. We defined intrinsic and extrinsic constraints on the stationary points of Vp based on whether they are independent of the coefficients in Vp or not. Stationary points form GFP orbits. Stabilizer of a stationary point under GFP generates intrinsic constraints. Symmetry group of a union of GFP orbits independent of the coefficients can be larger than GFP. We name this group G tilde FP. Stabilizer of a stationary point under G tilde FP also generates intrinsic constraints. We reviewed the framework of the auxiliary group where GF is given as the direct product of the conventional group GR and the auxiliary group GX. We constructed effective fields using the elementary fields. The stabilizer under G tilde FP generates intrinsic constraints on the effective fields. Such constraints in general cannot be intrinsically obtained otherwise. I would also like to mention that even though I have concentrated on the application of these concepts to flavor physics, they are relevant in other areas of physics where we have scalar fields transforming under some discrete symmetries, such as in cosmology where we have scalar dark matter fields, inflaton fields, etc., and also in condensed matter physics. Also, it seems to me that this existence of a larger symmetry group for the stationary points has not been explored in mathematics literature. If that is correct, these concepts are novel from a general mathematical physics point of view also. This concludes my presentation. Thank you very much for your time. If you have any questions or comments, please write to me or leave a comment here. Thank you very much.